right, so these are our notes here on types of radiation. So if you haven't already, go ahead and open up Classroom, and you want to open up here the types of radiation. I know it's not here right now because I'm recording right now, but the video will be here, and you're going to click on it, make sure it has your name. You're going to do your Cornell notes for types of radiation. The same way we've always done, make sure you do your essential question, and then you'll process your notes at the end, okay? All right, so let's go ahead and let's get started. So, types of radiation. So, our essential question for these notes is, what are the 3 types of radiation decay and how do you identify them? So, that is the biggest thing as we go through this, is that I want you to be able to look at an equation for radiation decay and understand what type it is, be able to identify them. So there's 3 types we're going to talk about here. The first one is alpha, and we designate it by this alpha symbol. These are Greek letters. The second one is beta, and the third is gamma. So this picture here is pretty important, so you can probably copy and paste this into your notes. But alpha is our weakest, and we'll learn about that in just a minute, and it gets blocked by paper or skin. Beta, the waves from beta, actually can go through paper or skin and are blocked by aluminum. And then the worst ones we'll talk about is gamma, and those go all the way through paper and aluminum, and they are the most dangerous, but they are blocked by lead, and that's why you have to use a lead cover when you take x-rays, because they are trying to protect you from the gamma rays. Okay, so let's talk about our first one. This is alpha decay, and you can see alpha has 2 protons are the red and neutrons are the blue. It is designated by the Greek letter alpha. This funny looking kind of A or infinity. I'm not sure what it kind of looks like to everybody. But this is the representative picture. This is what comes out from the decay. So this is what comes off of an atom. And it's written as a helium atom. Remember, we talked about this is an isotope of helium. It has a mass of 4 and an atomic number of 2. Because it has a 2, if you look on the periodic table, that's why we give it helium. But it has 2 protons and 2 neutrons. So this always, you will see this in an equation of an alpha decay. So what is another name for that symbol? Is helium, but only the nucleus. So it's not talking about any electrons or anything. Nothing of that comes off, but we call it helium because it has 2 protons, okay? It is the slowest and least powerful forms of nuclear radiation. It is blocked, as we saw in the beginning, by paper or skin, okay? And what it also is that particle that you just saw, that helium-4 is a positively charged particle with 2 protons and 2 neutrons. And it's emitted by the nucleus undergoing radioactive decay. What does that mean? That means it's breaking down, and what comes off is what we call an alpha particle. So this is kind of an example here. So how does alpha radiation change an atom? So we can start with this radium, which has an atomic number of 88 and a mass of 266. So when it decays or starts breaking down, okay, as it starts breaking down, what happens is a helium atom, or what we call an alpha particle. We do say helium, but it's not a complete helium because it doesn't have the electrons, but we call it an alpha particle. We write it as this, 42He comes off. So as you can see, what happens is the mass is 4, and look here, 226 minus 4 gets you 222. And 88 minus 2 gets 86. But if we add these together, we would add back up to radium. But it changes the atom from radium to radon because it pulled out those protons. So alpha radiation is identified if you ever see a equation of alpha decay. If you see a helium atom written there that comes off, then you know it's alpha. Okay, and you can see mass is definitely conserved, as you've learned in many of your science classes. So that's why it has to add up to the same. We can't make it disappear. So this is an example of an alpha decay reaction. All right, let's move on to beta. So It is designated by this Greek letter, beta. Looks like kind of like a fancy B. This is a picture of what comes off. What comes off is an electron, okay? So we don't lose any protons and we don't lose any neutrons. When we have an alpha decay, we have something come off in the equation and it looks like this, an electron. And remember, electron has no mass. That's why it's not included in the atomic mass. And it has a charge of -1. So we give it a charge of -1 because electron, there's nothing on the periodic table. So it doesn't really have an atomic number. So we just designate at the bottom a -1. Okay, and it is a greater speed and power than alpha particles, but stopped by a sheet of aluminum. So it's the middle. So it can go through paper, your skin, and then if you have aluminum, it blocks it, bounces it off. Okay. So it is a high-speed electron, or what we call sometimes a positron, which means it's a positive electron. Just know that that is a possibility. I'm not going to explain that. That's for as you go up into higher chemistry courses. Okay, and it's usually emitted when a neutron decays into a proton. So what does that mean? It means a neutron comes out of the atom, it decays off, and it decays into a proton. Or it can occur when a proton decays into a neutron. So just know that can happen. They can break down and they can change. Do we exactly know how it happens? Do we exactly know why it happens? No. So these are just things that we know happen and that we just kind of accept, okay? So how does beta radiation change an atom, okay? So I kind of took over, but it's here. So this is kind of an example of what a beta reaction would look like. So we start with lithium here. Okay, and it's got a mass of 8, atomic number of 3. It decays into beryllium and electron. And notice, this is the crazy thing, you don't have to figure these out, but notice that we have a -1 here and 0. Now the mass does not change because when we lose an electron, we don't change the mass. But what happens is a proton will so a neutron will become a proton, or a proton becomes a neutron, okay? So that's why the mass doesn't change, because those are both, it doesn't matter. They're going to be the same number of the same amount of protons plus neutrons. But this atomic number is going to change, because remember, atomic number is about protons. So why the heck does it have a -1? Think about this. 3 minus a -1 gets you 4. Okay, because we're subtracting this because it's decaying, okay? So it becomes this. And that's why sometimes you'll see what we call this positron. Do we know when it becomes a positron or an electron? No. But when it's a positron, it would be a +1. So a positive electron, then it's 3, okay, minus 1, which would be a 2. So that's when we get these two different things happen. And we can't predict if a neutron is going to become a proton and increase the atomic number, or if a proton decays into a neutron and decreases the atomic number. We don't know, but we just know whenever we see an electron. So if you ever see this coming off of an atom on this side of the right side, then that's your beta decay. All right, the last one we're going to talk about is gamma radiation. And it is shown by the Greek letter gamma. Looks nothing like a G, I know. Okay, and this is the representative picture. This is a gamma radiation ray that comes off. It's just a wavelength. And you'll see that on the equation sometimes. And the symbol we write, you know how we had the helium, we had the electron, now we have gamma. And gamma has no mass and it has no protons. It is just a wavelength, okay? And it's called a gamma ray, okay? It has the greatest speed and power of all 3 types of radiation decay, okay? And that I went a little fast. So it has the greatest speed and power of the 3 types. So it is the highest. It's the one that's only blocked by lead, if you remember, okay? It has a high energy electromagnetic radiation, and it's given off during radioactive decay. Okay, alpha beta fusion. So you see these come through as just a wavelength, and it's very damaging. Okay, so that's why we have to protect our body from it, because it goes through our skin, it goes through aluminum. But this is what we see happen when we actually end up with gamma. So we can start with, this is cobalt here, mass of 60 and 27, okay? It can decay, it can go through a beta decay where it gives off the electron, and then it can still go through a gamma decay. And so what you notice when we have that happen, it's like a bunch of energy. So what happens is it turns from cobalt to nickel, it goes through that beta, it's in an extreme excited state because now it's not balanced at all. Okay, and so by giving off this electron, so what happens is then it just gives off a gamma ray. So it releases all that energy, okay? And so that's when it gives it off in the form of a gamma, what we call photon. And those are extremely damaging to us and to many, many things. And so what happens, though, is you can see how it doesn't change the actual element. The other two actually changed what it was because it changed the protons. Well, because a gamma is a 0, 0, it has no mass and no atomic number, these numbers don't change. And this is the only radiation decay that does not change what the element is. It does not change the atom, okay? And remember, gamma radiation, is the only thing that actually made Hulk into Hulk, okay? Remember, he got hit by gamma rays, okay? All right, so let's do a learning check real quick. True or false? Alpha particles consist of 2 protons and 2 neutrons. So take a minute. What do you think? Do you think that is true? You can go back, look at your notes. It consists of 2 protons and 2 neutrons, an alpha particle. Hopefully you came up with true. Which of the following does not change the nucleus of the atom? So which radiation, alpha, beta, gamma, or all of them, does not change the nucleus, does not change what it is, does not change the protons? So take a minute. And I hope you all said, yes, gamma is the only one that doesn't change, okay? All right, so now I want you to go back to your notes. You're going to highlight any important notes. You're going to make connections to any of the notes in the left-hand column. You can talk about Hulk and how maybe you read a book about Hulk turning into Hulk, or was it Bruce Banner turning into Hulk from gamma radiation. You're going to write any questions you may have in the left-hand column. You're going to use your highlights, connection, questions for your summary, and then I want you to write a 3 to 5 sentence summary, and then turn that in. Well, that's it for gamma, or what is it, beta, nuclear radiation decay.